My name is Jack Shaw. I'm the district manager for the UK and Scandinavia. Thank you for tuning in. Today I'll be talking about in situ remediation of fractured bedrock, really emphasizing that this is something that can absolutely be done. The motivation for putting this webinar together was when I'm talking to people about different sites that they're looking at. Maybe they're undertaking a remediation options appraisal for one site, and they'll also say, oh, we have another one where we have toluene impact or PCE impact, but it's in a fractured bedrock. So I guess maybe that's not something you can help us with. Really, it's something that we absolutely can, but fractured bedrock sites do have their challenges. So we're going to look at those challenges, the solutions to those challenges, and then I'm going to draw on 4 separate case studies where we've used injectable substrates to remediate fractured bedrock sites to illustrate the success and the different ways in which you can remediate those sites. So yeah, we're going to look at, first of all, how we work as Regenesis and why this is important for bedrock sites. Many of you have logged on today. I had a look through the attendee list, and some of you may not have interacted with Regenesis directly before. And I'll just work you through how we evaluate sites, why this kind of consultation is important broadly for most remediation, but particularly for bedrock sites. We're then going to look at the challenges that come with fractured bedrock, delineation of contamination, and coming up with an appropriate remediation strategy. And then I'm going to point you to different resources that are out there for site investigation planning. Now, I will say I'm not an expert in this area. It's been a while since I've had to plan a site investigation on my own. But there are a wealth of resources out there that can really help you come up with different tools and techniques that perhaps aren't part of your standard site investigation suite. Finally, then, we'll end on a series of case studies looking at sites where we have remediated dissolved phase chlorinated solvents in a fractured bedrock system, where we have remediated sites where you have free phase petroleum hydrocarbon contamination, a third where we're looking at DNAPL concentrations of chlorinated solvents. This is a fairly early ongoing site that we're working with Rambol, where the results are looking excellent. The injections were actually completed in January of this year. And then finally, we'll look at a site where we remediated metals. We remediated hexavalent chromium plume with BRD Environmental, where we have over 2 years of validation monitoring showing the success of that particular site. And then finally, we'll end with a summary of remediation options and the strategies that you can draw on to treat bedrock sites in situ. As Regenesis, as a company, we've been around for a while, over 25 years, completed some 28,000 projects worldwide. Within the UK, Scandinavia, we certainly look at something between 20 and 35 sites a month. And I would expect 2 to 5 of those to be bedrock sites. So this is something that has absolutely been done many times before across the world in many different geological settings. And in order to make these solutions successful, this upfront consultation approach that we do is critically important. So first of all, we will review the site to see if it is appropriate for our remediation technologies. Now, Regenesis, we have a lot of different technologies, a lot of different techniques that we can deploy on a site, but that doesn't mean we're the panacea with the absolute solution for everything. It's important for us and for you guys that we identify if this site is appropriate for these technologies, or if there's just some gap analysis. So maybe if there's a little bit more investigation done, we can give you a more certain answer. We'll then help you with the technology selection. That selection of technology will not only be dependent on the conceptual site model of the site, but it's also going to be dependent upon the commercial landscape that surrounds that project. So are you looking to clean this site up very quickly because it's a development, so you don't have time to do a protracted enhanced natural attenuation program? Or are we looking, or actually do we have the time? You know, it's an active manufacturing facility. It's going to be an active manufacturing facility for many years. These sorts of things are going to influence what kind of technology we're going to recommend for that site. We provide you with a remediation design that will outline the cost, that will outline the injection configuration and the dosing, and broadly a program for the application and the remediation. Something that we do fairly routinely now, I'd say about 70% of the larger projects that we do are ones where we're offering a turnkey service. So we come onto site and do those application works for you, do those injection works for you. Very more often than not, we are subcontracted in by a remediation contractor, or we're contracted by a design and build consultancy. And then finally, post-evaluation. Now, we in REGENESIS, we don't do this. We don't do the sampling, we wouldn't do the report writing. That's always done by a third party. But we do like to be involved just to see the data that's coming through after these injection works have been completed. Really, it gives us the opportunity to see if sites are going well, if they could make a good case study. But equally, if something isn't going to plan, it gives us the opportunity to rectify that if you have a particular recalcitrant area on the site. So we're all about from cradle to grave support, and that consultation period for these bedrock sites is really important. And I'm going to illustrate this in a second. So the key thing when it comes to bedrock sites and broadly all in situ groundwater remediation is that there are always going to be known unknowns. And no matter how much site investigation you do, be it over tens of years, there's going to be parts of that site where perhaps there is a pool of DNAPL and it hasn't been picked up as part of the site investigation. Now, as long as this is acknowledged and there are appropriate contingencies put into place and everyone's expectations are managed accordingly, then this can make for a good and robust remediation strategy. Some of the things that are unique to fractured bedrock sites is how this contamination is going to be distributed in the subsurface. Contaminant distribution and transport is going to be largely governed by fracture flow. The extent of that contaminant transport is going to be dependent on fracture interconnectivity. And when you're designing your site investigation, I'd stress that this should be one of the major objectives for your SI, is to understand the interconnectivity of the fracture network on your particular site. Chances are, if you're looking for that, if you're looking to delineate that, to understand how this fracture network is behaving on your site, then what will follow is a plume delineation, because you'll find all of these preferential pathways, you'll find all of these flux zones that are going to be responsible for 99% of your contaminant transport, and you'll end up delineating your plume. With sedimentary bedrock, there's an added complication in that you are going to have contamination. The primary flux of contamination is going to be in your fractures, but you're also going to have a pool of secondary contamination in your primary porosity. So as that contaminant moves through the fracture, through advection and diffusion, you're going to get contamination diffusing into your primary porosity, into your rock matrix. And this is something that is going to be crucial to, one, understand, but also to communicate to all stakeholders, be that remediation practitioners or the liability holder for the site. Because while in the initial phases of remediation, you may see a significant drop in contaminant levels from remediating contaminant mass in the fractures, you have got this secondary source of contamination in the rock matrix. Within those fractures, you'll have reduced contaminant mass sufficiently, so you'll likely create a concentration gradient. Flick's law then says you'll get diffusion, so you'll get back diffusion of contamination from that primary porosity that will lead to, in some cases, a protracted lead-in time for cleaning up sites to particularly stringent criteria. So this is something to be thought about, to be communicated about, both at a regulatory level, so to establish expectations as to when this site is likely to be cleaned up, and also to the liability holder as to timeframes and maybe why you'll see a lot of action early on in those remediation phases, and then why maybe there'll be this protracted period of back diffusion. But back diffusion is not necessarily an obstacle that we can't overcome. There are many different engineered injectable substrates that can overcome this, and I'm going to talk about that as part of this presentation. The direction and flow of the contamination is going to depend significantly on fracture geometry. Sometimes the contaminants will be behaving in ways that you wouldn't expect them to. I reviewed a site a couple of years ago in a Bromsgrove sandstone where we were dealing with free-phase petroleum hydrocarbons. These the free phase, however, appeared to be diving, and that was down to the fracture configuration dipping on the site. So this is, again, something that's super important. With these hard rock sites, your site investigation and drilling is going to be costly. So when it comes to planning this, you want to try and make sure that every well on your site is working as hard as possible for you, so you can better not only delineate and understand the conceptual site model, but also try and take the opportunity to use this infrastructure as part of your remediation strategy. So as I said before, sort of how we work in Regenesis, it's not always a case that somebody comes to us with a completed site investigation and says, there's not going to be any more investigation, this is what you've got, work out a solution for that site. For complicated fractured bedrock sites, what often happens is the first and maybe second phase of site investigation has been completed, and that we're now into another phase of remediation design characterization. So there's going to be a third phase of site investigation focusing on better understanding the site in terms of remediation. This works very well if you can get a remediation practitioner on board sort of ahead of finalizing a remediation strategy. Often we will be looking for things that may not, that a consultant who is focused on risk and delineation may not be looking at. We can help you with how to construct monitoring wells or delineation wells that may not be used as part of the validation strategy. These wells could then be utilized for abstraction using a pump and treat system, or they certainly could be used as injection points as well. So it's all about capturing and generating as much value from those costly monitoring wells so that they can be used as part of a remediation phase as well. So engaging with remediation practitioners early on, as this sort of cost time graph shows you, can save you both time and money in terms of the total project cost. Something I will stress is that for these fractured bedrock sites, you do need an experienced geologist to be there logging those cores. It's fairly standard in our industry that you see that brand new graduates, the first thing that they do, they're sent out to site. It's important that they are 100% billable, but they may not have the experience of working in fractured bedrock settings. So I would always stress, if you can, if the budget allows, do have somebody more experienced on site. If you can, get them both on site, so there's could be some cross training, so they can understand what they're looking at and what they're logging. But these kind of complex fractured sites, the best ones that I have worked on is where there is a multidisciplinary approach, where you have people not only from the land quality group, but people that have drawn on from geotechnical that perhaps have a slightly different understanding to this than us in the contaminated land profession do, as well as water resource hydrogeologists that will bring another angle to these to the discussion to then better delineate and understand what's going on the site. So they're very much one of these where you need to draw on as many people as possible. And, you know, we in Regenesis, we're here to help as well. It's fairly routine for me to be involved in these sorts of discussions. So don't ever hesitate to give us a call, even if it's just to bounce around an idea. So in terms of the solutions, what do we in Regenesis need to know in order for us to provide you with an in situ remediation design? So this can broadly be broken down into 4 categories. These are the importance of which, you know, we're going from top to bottom. We need to understand the geology, because this will define flow regimes, and we need to understand hydrogeology, because this is going to influence flow and transport. And together we can, with these, we can understand the contaminant flux. Now, one of the methods that I favor, and if it's technically feasible, when it comes to fractured bedrock sites, is the installation of permeable reactive barriers, or a series of permeable reactive barriers, or PRBs, across the site, utilizing what can sometimes be quite a high flow regime, so something with a significantly high seepage velocity across the site, to provide sequential treatment. As that plume moves across the site, you get comparatively cleaner water than migrating off-site, so you're managing risk that way. It's not always possible, but it's a method that I favor because you're ultimately installing less wells, and if you're looking to treat at depth, it's going to be the drilling that's going to be the major cost rather than the reagent and the application. So a series of PRBs can often mitigate against that high drilling cost. Similarly, geochemistry and microbiology is very important in fractured bedrock sites, particularly if the contamination is at depth. The reasons why natural attenuation may not be occurring at depth can be quite complex. It's something that we see quite often in fractured, say, crystalline granite, for example. You may have a PCE spill from a former dry cleaner. That spill happened some 30, 40 years ago, but there's very little evidence of natural attenuation occurring. You have to ask yourself, well, why is that? It could be that you have very high flow of groundwater moving through this system, so you're getting lots of aerobic water that is inhibiting that reductive dechlorination process. It could well be that you're dealing with quite a barren system, so there isn't much micronutrients down there. So that could be in the form of, if we're sticking with the chlorinated solvent theme, electron donors. It may be that they are lacking in micronutrients such as B12 and other dissolved metals. So these things need to be established in order for us to know, do we just need to inject an electron donor into the subsurface, or is there something else that needs to be added to kickstart that natural attenuation process? Similarly, microbiology is important, particularly, like I say, if we're looking to treat at depth. When I say at depth, I mean, every site's different, but I would say if you're looking at 10 meters and below, then these things really start to come into play. I recently, well, not so recently, a couple of months ago, I looked at a site where they had completed some qPCR analysis of the microbial consortia across this site. I think it was something like 1,500 square meters, so it wasn't a particularly large area. But what I did notice was 10 meters apart, you had one well where the cell count of the D. halichoides and D. halobacter bacteria was really quite high. So high that I had assumed some kind of bioaugmentation may have happened ahead of these guys getting to site. But then you go 10 meters the other way and you're dealing with really low populations of these microbes in the subsurface, but similar levels of contamination. And it could well be that we're dealing with two different fraction networks. One may be drawing on deeper water with less electron donors and other micronutrients, whereas the other is part of a different fraction network where these nutrients are abundant for whatever reason. So these are the sorts of things that you need to look at, and they will inform what you would inject where. In terms of tools that are out there, as I said, I'm not an expert in different site investigation techniques, but what I will say, there's an abundance of free information out there that is available from the ITRC and other regulatory websites that can help you come up with additional ideas to better characterize the site. This one is a site investigation matrix. You can input a series of parameters. So here I've done hydrogeology, bedrock that's saturated. I'm looking for semi-quantitative data. You hit search. What appears to be quite a lot of macros whirring in the background because it's taken my computer a while to come up with the answer. So if you just zoom in there, you see that it tells you where it's what it's applicable for. So geology, hydrogeology, chemistry. And then in each of those techniques, you have a hyperlink that then tells you more about that particular investigation investigation methodology. Now, take a screenshot there if you need that web page. Another way of doing it, I think if you Google ITRC Investigation Matrix 1, probably put DNAPL in there as well, you'll likely get to the page where you can download this. But it's a tool that I was quite impressed with. Cluein is another website, I would say, packed with full of really useful resources. Maybe if you're listening to this and you're just starting off in your career, there's lots of webinars out there that can really kind of open your eyes to how to do different things on these sorts of sites. With regards to the reagents that we're injecting then, how is it different on fractured bedrock sites? And then crucially, how are we REGENESIS slightly different on when it comes to the reagents that we offer? So the reagent flow will be faster on fractured bedrock sites than in superficial deposits, so soils, silts, sands, clays, things like this. This has an advantage though. It means that you will have a higher radius of influence. You may be injecting across a fracture aperture that isn't particularly wide, so you'll be injecting under fairly high pressure, so you'll be able to get better advective distribution from your injection well. So that's a positive thing. But the reagent will be more diluted. This is something we would need to keep into account. This is something that we would need to take into account when it comes to the design of that solution. So this is why understanding the fractures, the size of those fractures, the frequency of them is really important. There's also going to be less matrix interaction, and this kind of goes both ways. So there's less matrix interaction, so it could be more susceptible to changes in pH. This will need to be managed. You're going to have less sorbed contamination. This is particularly true for crystalline bedrock, where you don't have issues of diffusion into primary porosity. You're going to have reduction in matrix retention of both the reagent and also the contaminant. Again, could be a positive though, if most of that contamination is in the dissolve phase, is in the water, then using chemical reduction or oxidation technologies may yield quite a rapid reduction, as you're not dealing with that excessive amounts of sorbed phase contamination. And then finally, you have a reduced surface area interactions between the reagent and the contaminant. However, this can all be ameliorated by the fact that the product will have been placed across a wider distance. So the contact may be greater as you have this wider radius of influence or distance in the direction of the groundwater and the contaminant transport. So it can work both ways. But what I would say is the choice of substrate is going to be really important. If you are a remediation contractor, or if you are a environmental consultant and you're auditing, if you like, the different options you have out there, I would argue that these are the 4 key things you need to look at. So the first is distribution, and it's obvious why that's important. If you're injecting something into the subsurface, you want it to distribute far, but not too far, because that will reduce the number of injection wells you're going to need to install into this hard rock. Second is persistence. So because the reagent flow will be faster in fractured bedrock than in superficial deposits, you want something that is appropriately soluble. You don't want something that is going to wash away and require multiple injections. You want something that's going to hang around, but also be appropriately reactive. So an example would be vegetable oil. If you were to inject vegetable oil into these settings, it might be persistent, but it will take a while to start fermenting. So you haven't got something that is appropriately reactive. And then finally, and I'd argue that this is probably the most important thing, is ease of use. Because if you've nailed the other 3, but it's a nightmare to use on site, it's not being injected as it should be, it has high issues when it comes to health and safety, and I've seen that with some zero valent ion technologies, then it's a non-starter from the beginning. So making sure all of those 4 things are balanced is going to be really important. In terms of application technique, something I'm often asked is, okay, how do you stop all of your reagents just disappearing down one fracture? one large fracture rather than get it with disappearing down one large fracture, and ensuring that you get an even distribution of that reagent within your treatment zone. So there's a number of ways you can do this. We probably more often than not, rather than the picture that you can see here, we would favor nested well installations if that's possible, where you have maybe 3 wells with 3 meters of slots installed at different levels to sort of mitigate against this concern of all the reagents flying down the single fracture. It may well be that that's what you want it to do. It could be that you're dealing with a site where you have a single fracture system. If you can just intercept that, you can address 90% of your contaminant mass, but that's going to be fairly unusual. So another option would be to install an injection well similar to this, where you have these 3-meter lifts. You drop a double packer down those wells, you inflate them, so you're isolating those 3-meter horizons, and then you're injecting under pressure to ensure that you aren't just, as I say, injecting all of that reagent down a single fracture. With regards to application configurations, there's a number of different ways that you can do this. I've just illustrated 4 of them. As I said, I personally favor sort of multiple in situ PRBs across the site, so a barrier configuration. I think it's a nice compromise between the cost of drilling and then the speed and efficacy of treatment. Not always applicable though, particularly if you have quite a slow moving groundwater regime, but that's seldom the case in fractured bedrock sites. Another option would be recirculation. So the drilling cost there would be relatively low, but I would say it is probably your higher risk of it not working. You'd certainly have to do a pilot trial, maybe with a reagent, maybe with a tracer, to ensure that there is conductivity between your injection and your abstraction well. While you may save on drilling, you've got operational costs in there. Someone's got to manage and maintain that recirculation system, so that's something that has to be thought about. But it's certainly something that could be considered, particularly if you're on a site where you have buildings and it's not possible to drill inside. Using some kind of recirculation system to drag a reagent beneath that building to ensure even treatment could be an option. Drift and inject could be useful for some colloidal technologies that we will talk about. However, it's not always a good idea to do this. We in Regenesis have mechanisms to control the spread of our colloidal technologies, but it's certainly an option that is out there. And then finally, grid pattern injection. So that's the most expensive, but it's the most expensive and it gives you the greatest certainty of results. If you're injecting many more wells, you're doing it as a grid across your whole plume, you would expect to see pretty rapid cleanup quite quickly, but that is something that you pay for. Indeed, with these sites, often I find that it's a combination of barriers as a standalone technology, or it's barriers with grid applications where there is good delineation of that contamination in that fracture network. Indeed, the case studies that I'm going to present to you, the first 2 are 2 case studies where we've used in situ PRBs, and then the second 2 is a combination of in situ PRB, so in situ permeable reactive barriers, with grid applications across known hotspots and source areas. So the first 2 case studies then, these in situ PRBs, the first one I'm going to talk about is actually one that we recently had a webinar on. Emma from Golder kindly agreed to co-present this. I think this was sort of just back before the summer. So if you are interested in this particular case study, on our website, we've got this recorded. Emma does a much better job than I will of explaining the site and the history, rather than the 10 minutes that I'll take you through this one. But the site itself is an active design and engineering site. It has been since the 1960s. It did have a series of previous uses though, so it was greenfield, it was a farm before that. but it was also an airport / aerospace facility where they developed light aircraft and bombers. The site is located on the edge of the city with two rivers running close to the site, sort of acting as site boundaries, really. And there was a known use of historic solvents, some of which were reported, some of which it would appear not, due to the age. And as such, a fairly extensive site investigation phase was completed from 1998, really in various stages up to about 2016. There was clear evidence of TCE found, and this spurred on these further phases of site investigation, which amalgamated into 150 boreholes drilled and installed across the site. This included your standard 50 mil wells, as well as dual installations, CMT3s and CMT7s. The culmination of this work showed that we had some superficial deposits, though I believe they weren't that heavily impacted. They varied in thickness across the site. We are looking at quite a large area that had been investigated here, between 1 and 4.5 meters. The bedrock was interbedded sandstone and mudstone, so pretty complicated, that was fractured. Those sandstones dominated at the higher elevations, and what was found was that it was the fractures in the bedrock that was the primary flow mechanism for the DNAPL, for the DNAPL through the aquifer. So as part of our, I'll step back one, as part of our remediation strategy, we were suggesting that, let me get my laser pointer, that source zone treatment using a appropriately soluble electron donor should have occurred here, and then a in situ PRB comprising plume stop and another electron donor called HRC was to be installed along the down gradient edge of the site to protect the stream. So the results I'm going to show you is from a very early pilot trial from 2016. The pilot trial comprised about a 10-meter barrier where we injected plume stop in combination with HRC. Here you have two additional wells that were installed, GA1601 and GA1602. 01 was our up gradient well, so our control, if you like, and then 1602 was our target well. GA1615, this was a pre-existing well that gave us some historical data. The technologies that were installed, so the first one was plume stop. Plume stop has been around since 2014 now. What it is, it's a finely milled granular activated carbon that's been milled down to 1 to 2 microns. So that's the size of a bacterium, that's the size of a pore throat. And what we've done is we've coated this granular activated carbon in a dispersive polymer so that these carbon particles flow and behave in such a way that they don't stick together when they're injected into the subsurface. They repel each other, but they stick to the aquifer matrix, so they can paint the subsurface with carbon. This dispersive polymer means that they behave and act as a colloid. So blood is a colloid, wine is a colloid. They move very freely in the subsurface. So distribution, really important here. Fractured bedrock sites, you don't want to be injecting hundreds of wells to get interconnectivity of radius of influence. Though sometimes that is necessary with these sorts of with these plume stop jobs where you are dealing with very high contaminant loads. But here we had lower dissolved phase concentrations. We could get away with wider spacing. Just to illustrate how well it moves in the subsurface, here you have plume stop on the left, and then you have powdered activated carbon on the right. This is just an experiment done at our R&D facility in California. You can see here that the plume stop migrates right the way through. We just flush 14 pore volumes through that column, whereas the powdered activated carbon doesn't move very far at all. In terms of distribution of the reagent, here you can see a before shot. So these are sand grains, very flat, not a lot of absorption sites. In these fractured bedrocks, it's important to remember that you will have maybe cemented sand or even weathered sand particles that are in the fractures. So there is going to be some matrix for this to absorb onto. Afterwards, after applying the plume stop, that coats that sand grain, greatly increasing its surface area and greatly increasing its absorption capacity. We then would pair it with an electron donor to create an environment conducive to reductive dechlorination. The microbes that are responsible for reductive dechlorination, they're not planktonic, they're sessile. They sit on the aquifer matrix and they secrete a biofilm to capture and metabolize that contamination. But by using the plume stop, we've absorbed those organic contaminants onto the plume stop matrix. We have then added an electron donor. The electron donor in this case is a technology called HRC. Comes in a series of strength, I guess, if you like. The primer is used to prime an aquifer to create anaerobic conditions very quickly. You then work your way up to HRCX, which provides a controlled release of hydrogen for up to 48 months. So combine these two, what do you get? You get wide distribution of plume stop, really important in these fractured sites. You get contaminant absorption, which then promotes the growth of a biofilm. That then promotes biological degradation. When you pair it with an electron donor, that is accelerated more. In this case, electron donor is in the subsurface, so you get enhanced reductive dechlorination. And the key thing is that as those absorption sites get freed up, more contamination can then resorb onto the plume stop, which then deals with further influx or back diffusion of contamination. As I'm talking about this, maybe there'll be time if I can scramble and find it. We did a really interesting experiment looking at we did a sand tank and it was filled with permeable sand and then fairly impermeable clay, and plume stop was sent through it. And you could see that the plume stop actually diffused into those impermeable clay layers. And to a degree, you could expect that to happen depending on the geology into the bedrock. And then around and around you go. So you can engineer a self-cleaning Brita filter in the subsurface. In terms of our results, so these are the down gradient wells. You can see here that there was some pretty dramatic drop-offs after the plume stop had been injected. Works very well with the chlorinated solvents, not only things like TCE, which do have a pretty high affinity to carbon, but also vinyl chloride as well, sort of just above the detection limit. Something else that we had in this plume was benzene and MTBE. That wasn't the target of, these weren't, the target of our treatment. MTBE in particular, we were kind of managing expectations really. MTBE is a fuel oxygenate. It's not particularly toxic, but at pretty low levels it can taint, it can make your drinking water taste bad. So there wasn't a particular risk driver for this one, but it also doesn't have a particularly high affinity to carbon, but we were able to reduce MTBE levels down to non-detect as well. So that was a bit of a result. In terms of the other case study, so this is one that we did with Jacobs. This was an active factory. So unlike the site that we did with Golder, where most of our work really was done sort of off-site, though within the red line boundary, if you like, here we were very much on an active site. There was a series of spillages of honing oil. So this is a heavy oil. It's a lubricant that had infiltrated through the vadose zone into the groundwater via fractures, impacting the underlying chalk. Here we had very high levels of dissolved phase contamination that would suggest in excess of solubility, and we did have some L-NAPL as well. So a pretty heavily contaminated site. Here we utilized existing wells on site to apply the reagents into the subsurface. There was already quite a dense array of delineation wells, and based on the validation strategy that Jacobs came up with, we could sacrifice some of those wells for injection wells. So that goes back to us, trying to utilize the infrastructure that's already there to keep remediation costs down. So what we initially did, we injected a product called PetraCleanse into the subsurface. We did this across the wells where there was the most heavy impact, where there was measurable free phase. We were lucky here, we were able to utilize a vacuum tanker to remove the desorbed contamination, as we had pretty good recovery rates from each of those wells. Just to illustrate how PetraCleanse, sorry, we have far too many products that start with PetraCleanse that works. Typically, we would pair it with some kind of physical abstraction system. So in this example, we're looking at a pump and treat system. In the case study, we did this with vacuum tankers. So the other site, you have free phase sat on the groundwater. The first thing that you do, if you have measurable free phase, the most efficient and appropriate thing for you to do is to pump it off. You know, it's at this point that we can't really help you. But the thing is, as that pumping regime goes on, you get progressive desorption. And that desorption can lead to asymptotic recovery of contamination. Something I will say is that to use Petrofix, you need a total fluids recovery system. Skimming alone won't help. Won't be compatible. So to overcome this, essentially you're dealing with a system once that asymptotic recovery occurs, where you have most of your contamination now bound to the soil and diffusing into the aquifer. You then add PetraCleanse, and what it does is it raises the pH of the groundwater to pH 11, and it partially chemically oxidizes the petroleum hydrocarbon molecules in situ. Now, because we've raised the pH, we've reduced the charge, which means that these polar molecules, so one half wants to be in the soil, the other half wants to be in the groundwater, can't resorb to the soil, so they bunch together to form a surfactant, and that surfactant can then be recovered using a pump and treat system. So once you inject, typically targeting the smear zones of the upper element of the aquifer, you leave it 2 weeks, allow that desorption process to happen. It's after 2 weeks that the pH will start to buffer out fairly quickly, and actually you can end up with resorption of contamination. So that 2-week window is important to keep an eye on. And with PetraCleanse, your recovery rate would tend to look a bit like this. So you'd have 3 desorption events, each progressively less dramatic, and followed by 3 abstraction events. Your final desorption event likely below your cleanup target, and then you continue to pump, turn system off, and crucially what you're not seeing there is rebound from the absorbed phase contamination. So it's a way of ensuring that, you know, you turn that system off, you demobilize it, go back and monitor things maybe not quite as you left them. So it's a way of mitigating against that risk. So elsewhere on the site, we utilized Regenox, where contaminant levels were pretty bad, but wouldn't warrant the requirement to undertake enhanced abstraction. And we also then injected across this area using ORC, so this oxygen releasing compound. Regenox as a technology is probably used every working day across the UK. It's a 2-part product. The first part is a bicarbonate-based chemical oxidant, and then the second part is an iron silicate catalyst. You mix them 1-to-1 with water. You mix part A to part B at 1-to-1, then you dilute it at about 5% of water. Here, the illustration showing direct push injection can absolutely be injected into wells. It certainly can be applied into excavations. And the key property of Regenox, and it was why it was chosen on this site, was that Jacobs were very health and safety conscious, and the client even more so. And this technology is very safe and very safe to handle and very straightforward to apply. It also has a significant longevity. So once injected into the subsurface, Regenox will continue to be active for up to 4 weeks. So unlike commodity oxidants, where you could be expecting a week to days of reactivity, once in the subsurface, it will be active for up to 4 weeks. What this means is you get better treatment. Chemical oxidation as a process depends on contact. The oxidant and the contaminant must make contact with each other in order for that chemical oxidation reaction to occur. So if you have something persistent in the subsurface, you're more likely to yield better treatment efficacy. It was important here, even though we were injecting at depth, that it wouldn't impact any underground services. So this included plastic pipes, metal pipes, cables, and foundations. In terms of the oxidation mechanisms, there are three primary ones. This is where the oxidant makes direct contact with the contaminant. That exchange of electrons then breaks apart chemical bonds and destroys your contamination in situ. Similarly, the propagation of free radicals, so the part A in the presence of ambient salts and metals will start to degrade and produce these free radicals. These free radicals are essentially molecules with unpaired electrons and will, when they come into contact with the contaminant, they will oxidize it and destroy it. And then the third final one is with Regenox. So this is the part B, this is the iron silicate catalyst. This is important because the part A is initially activated through base activation, but that pH is very quickly buffered out in the soil. As that pH starts to drop, this iron silicate catalyst will be formed and will act as a surface where the oxidant and the remaining oxidants and contaminants make contact with each other to yield better treatment efficiency. So those are your three mechanisms there. We also polished it off with a biopolishing step using ORC. That's our oxygen releasing compound. It's been around for a long time now, probably a good 20 years. ORC, when you apply it to the subsurface, it's a calcium oxyhydroxide where we've interpolated phosphate crystals into that structure to give you a controlled release of oxygen. So you apply it to the subsurface and it starts to dissolve. As it dissolves, it will release oxygen into the dissolve phase where those microbes can utilize it for bioremediation, so as an electron acceptor. Those phosphate crystals regulate the release of oxygen. So after a single application, you get up to 12 months of oxygen release, so you don't have to do multiple applications. And they also ensure that you don't have this impermeable rind forming, so that you do get that continual 12-month release of oxygen into the subsurface. That means that single injection, you're creating a stable environment over a long period of time. That means you grow a large microbial consortia that ensures that you grow a large microbial consortia, to break down as much of that contamination as possible, all from a single injection. In terms of our results, fairly dramatic. You can see that we were dealing with up to 18,000 micrograms per litre of this honing oil. That was reduced fairly dramatically. You can see here that the ORC is then taking an effect, and you can see that concentrations get low enough for this particular site where it was de-risked and no further action was taken. So the final case studies 3 and 4, here we're looking at a slightly different application configuration where you have a grid in the source area and then a PRB to manage off-site or on-site migration. So this is an ongoing site. This is one that we are doing with Rambol. We did the injection works in January of this year. Actually, one of the first sites where we've used a new technology called S-Micron ZVI. Again, another former airfield where they seem to be all about using TCE that had impacted the underlying groundwater. Two principal areas of impact. We had area A, fairly small, 350 square meter area, and then area B, where we had really quite high levels of TCE and DCE there. These are in milligrams, so pretty high concentrations of these chlorinated solvents. The geology here was very challenging. So this was a limestone bedrock. It was a cornbrash formation. So there were some fractures, but in cases not many. So it was important to understand where they were and target them appropriately with these reagents. There was also quite a varying groundwater level, actually not across that big of a distance. You could have had one injection well 4 meters away and there would be a meter difference in groundwater levels. So it's quite a complex regime. Hydraulic conductivity as well varied really between 0.5 to 5 meters per day. So our injection strategy in area 1 was sort of a grid injection across 2 hotspots. The bit that you can see on the left there, that was a hotspot quite close to the entrance to the site. And the area 2 strategy was a series of permeable reactive barriers. Those black rectangles there, that's just me protecting the street names. This is a confidential site. We can't identify exactly where in the UK it is. Here we injected an electron donor called 3DME. 3D stands for three donors, 3 electron donors. This is a molecule that we invented. It's a polar molecule. This is the 3DME molecule. Here you have a glycerol polylactate with an ester bond with fatty acid stuck on the side. So you end up with a polar molecule. When you mix it with water, you create these micelles. And these micelles are critical. One of the key benefits of 3DME is that these micelles enable it to be self-distributing. It's actually a technology I do often reach for fractured bedrock sites, because how these micelles work, you inject them into the subsurface, and about 300 ppm concentration of 3DME, these micelles will form. They'll travel down the aquifer, concentration levels drop. They'll then stick to the aquifer matrix, concentration levels increase, micelles form, travel down, stick, form, stick, form. So they can distribute very long distances, greatly reducing your drilling cost in fractured bedrock sites. It's also engineered to be appropriately soluble, so it's not going to wash out either. And once injected, it will continue to release hydrogen for up to 5 years. So you can create a really stable environment with this technology. We also co-injected it with S-micron ZVI. So S stands for sulfidated and ZVI stands for zero valent iron. At the time, it was the largest S-micron ZVI project we completed in the UK. What it is, it's another colloidal product like Plume Stop, where we've milled sulfidated zero valent iron particles down to less than 5 microns, and we've sulfidated the outside of that and suspended it in glycerol. This can result in, when you pair it with an electron donor, abiotic degradation and ISCA enhanced biological degradation. The reason why we've sulfidated it, you may have come across other ZVI products before. We've sulfidated it to reduce passivation. So ZVI in its raw form wants to react with everything. It's an incredibly reactive reagent, including water, which results in hydrogen being produced. If you sulfidate it, however, you can divert that electron exchange. So if you look at the second image there, sort of kind of like half a pie chart, if you like. On the right, you have non-sulfidated micron scale ZVI. What you can see there is 92% of those electrons go to react with water, with about 8% reacting with the chlorinated solvent. If you flip this, 87% of those electrons go to react with the chlorinated solvent, and only about 13% go to react with water. That 13% isn't necessarily wasted. That can be useful in rapidly acclimating an aquifer, for example. As a technology, we would reach for it on sites where you have higher concentrations of chlorinated solvents, particularly parent compounds, so PCE and TCE, and I'll come on to that in a second. The key thing with this is it distributes really well. I'd expect at least a 3-meter radius of influence in superficial geologies. Fractured sites, it might be further if we can inject it under a high enough pressure. Here you can see this is commodity ZVI, comes in much bigger particle sizes. I mean, it's iron, it sinks, and that's what it's going to do in your fractures. It's not going to distribute very far. Whereas S-micron ZVI, which is at 5 microns and below, and it's a colloidal suspension, you add it to water, you can kind of see it blooming there. You agitate it to create this colloidal suspension, and it will migrate much further in the aquifer. Much like in situ chemical oxidation, in situ chemical reduction relies on contact. So the better radius of influence that you get from your zero valent iron amendment, the better treatment you're going to yield as well. So what do you get with ISCA assisted bioremediation? Well, initially you're injecting the 3-DME. That starts to dissolve, and as it dissolves, it releases lactic acid. This lactic acid is then utilized by a different group of microbes, so fermenters. They break this down, and that produces the hydrogen. So that's the hydrogen. It's going to be used as an electron donor by another group of microbes called dihalococoides. These will utilize the hydrogen, um, exchange it for a chlorine atom. That exchange releases the energy that they need to live. And as they do that, they're reducing, here we are from TCE there to DCE to vinyl chloride, then eventually through to ethene. But the key thing with ISCA assisted bioremediation is that the PCE and TCE reduction actually goes down a beta pathway where it's reduced through to acetylene. That means that you mitigate against the amount of daughter products being produced, and that's a good thing because these daughter products are more toxic and certainly more mobile, and actually can to a degree be recalcitrant in terms of the rate at which they degrade. So sometimes you can see some DCE stall. Isn't often a problem for us with 3-DME. 3-DME has been engineered to be appropriately soluble. So you're getting that continual release of hydrogen for a 5-year period. So often we can chew through that. But the addition of S-micron ZVI can greatly increase the rate of degradation on your site, minimizing daughter products. Its delivery is very simple. This is it being pumped into a 3-DME mix. So there's no need for, I don't know, compressed gas and specialist mixing techniques. This is just add water and inject. So in terms of the results, so this is from area 1. This is the grid treatment. This is very much still in progress, but it's always good to show one that's super recent. You can see that the S-micron ZVI did a great job at removing the TCE. Here in June, we saw the peak amount of DCE in that process. That has then dropped, but we're seeing quite good levels of ethene being produced, which indicates that full dechlorination is occurring. The September results, which I actually received about 2 weeks ago, looking fantastic. And I think we're starting to look at the drop of DCE. We're then going into vinyl chloride, but again, more ethene is being produced. So excellent results. If you look at this in relative proportions of chlorinated ethenes and ethanes based on the geometric mean of molar concentration. So big thank you to Richard Bewley for passing these on to me. Just illustrates, this is what we were starting with in January in this area. We then moved through to June, July, and then eventually September, where ethene and ethane are dominant there. Similar story in area 2. So we've not seen this massive reduction, well, the complete reduction in TCE that we saw in area 1. So if you remember, area 2 was the permeable reactive barrier configuration. Still some very good results though. We're starting to see the vinyl chloride peak come through in September, and we're seeing increase in ethene production. Again, drawing back onto these, you can see as this is progressing, DCE is dominant, but ethene and ethane is increasing. Oh, I haven't got the September one. The reason for this is that we've essentially installed a permeable reactive barrier, in situ permeable reactive barrier, up gradient of the targeted monitoring wells. So this is just an illustration of what's going on. So you've got contaminated water advecting into the barrier, comparatively cleaner water coming out of it. That wave of cleaner water is going to take a while to reach that monitoring well. So there is going to be a bit of a delay. And one of the problems that you will have is back diffusion. And in this case, it's from primary porosity into the fractures. So the fractures you can see are the kind of mauvey red color there. And then the blue would be your primary porosity, your rock matrix. So as that back diffusion continues, as that concentration gradient becomes greater, you'll start to see cleaner water advecting away from the barrier. You've still got contaminated water up gradient, and it's going to take a while for that to fully be realized in that down gradient well. But once it is, you'll start to see full cleanup. So with these permeable reactive barriers, it's really important to have that conversation up front, not only with our clients, but also with the regulator and the liability holder, so that they understand that, okay, in some areas you may see a slam dunk and you're seeing great progress. In other areas, it might take a little bit of time because of this problem of untreated contamination down gradient of that PRB. But it's fairly easily explained. Finally, then, I am aware that we're running over time a little bit. Chromium-6. So this is a site that we did with BRD Environmental. It was a former sawmill where there was extensive Chrome-6 contamination up to 15 milligrams per litre on the site. Here we had weathered and fractured limestone. We installed a series of wells, one in a grid configuration at the source, and then a second as a permeable reactive barrier down gradient of that source area. Here we co-injected 3DME, so the technology that I introduced to you before, with MRC. So MRC is a benign organosulfur compound, and it's used with 3DME to alter the valency of chromium-6, dropping it down to chromium-3, precipitating it out as a stable sulfide, so it's no longer mobile in the groundwater. So we're not getting rid of the chromium. You know, it's a metal, we're not alchemists. We can just drop that valency to essentially make it immobile. In terms of the results here, I think these are sort of speaks for itself. Oh, this is 2014 we did this then. So injected the product in 2014, 2 years of monitoring there afterwards that shows that concentrations, well, dropped down to non-detect within 2 months and pretty much stayed that way for quite an extensive monitoring period across that site. And that was in a fractured limestone bedrock. So in conclusion, this is a matrix that I've adapted from the ITRC. This is where they are recommending that you can use different technologies. So you can see here you've got long-lived oxidants, which is broadly what Regenox is. You've got long-lived reductants, which is what S-micron ZVI is. And then you have controlled release substrates, which 3DME and ORC would fall into that category as well. And that broadly shows that you can use these sorts of reagents across various geologies. According to the ITRC, coal looks like it gives us some issues. So these are kind of sites that perhaps I can't help you with. Could do maybe with ORC and 3DME. Where you can use permeable reactive barriers, roughly where that says yes, again, we could look at exploring the use of something like Stop to do that. So I come across mainly sedimentary rocks, carbonates and clastics. In Scandinavia, we mostly come across intrusives, so granites and other crystalline bedrocks. So these technologies can absolutely work on these sites. And again, this is a third-party assessment, not necessarily of our technologies, but of long-lived oxidants, long-lived reductants, and controlled release substrates. So in conclusion, the in situ remediation of fractured bedrock using the fractured bedrock aquifers using injectable substrates, it's not new. It's been tried and tested many times. There's hundreds of case studies out there showing its possible use. But subsurface characterization is expensive, but will yield massive project savings. Your focus needs to be on fracture geometry and interconnectivity so that we know exactly where to target our remediation efforts. But ultimately, there needs to be the exception of, you need to accept that there will be known unknowns and that you should plan accordingly, be that in contingency, in a contingency sum that may be drawn on, maybe it's in additional investigation or negotiated regulatory closeout. When you are choosing reagents, it goes back to these cornerstones. Ensure that they are easy to apply, appropriately reactive and persistent, and crucially must distribute well and stick around in these high flow fracture zones. And, you know, reach out to remediation specialists. I mean, the key thing, not only with fractured bedrock sites, but really our whole industry, is to try and get as many different people in the room as possible with different expertise, and often you'll come up with the best solution. If you want more information, we have well over 200 case studies on our site. Just stick in bedrock, hit search, and you will find a wealth of information. Many of them are on that I've talked about. Well, all of them that I've talked about are on there in far more detail. But we've also, enough content here where you can search by industry, products, country, etc. Try and make it as transparent and easy for you as possible. So that's everything.
That's great.
Thank you. Yeah, thank you for your
Thank you,
time.
Jack.
Yeah.
That was a lot crammed in an hour. I am aware we're over
Yeah.
time, but I've looked at some of the questions that have come in and they're quite interesting. So I was going to try and see if we can answer at least a couple.
Okay.
But before we do that, just very quickly, after the webinar, you'll receive a follow-up email with a link to a short survey. If you're familiar with the webinars, you'll know about this already, but we really appreciate your feedback. So please take a minute to let us know how we did. And in the survey, there's also a space to request certificates of attendance, which may contribute to continuing professional development, CPD. So if you'd like that, please fill it in by clicking the link in the follow-up email. And also just to remind you again that after this webinar, you will receive a link to the recording as soon as we can make that available if you have missed any of the last hour. Right, so have a look at the questions. First one, any issues with different rock types? For example, is it easier to remediate crystalline bedrock versus sedimentary?
Yes, I'd say it probably is if the characterization has been done well. With some crystalline bedrock, you are unlikely to have that problem of back diffusion. They're going to be fairly impermeable. You may want to be reaching for maybe not enhanced bio, but certainly ISCA and ISCO technology. So yeah, it's certainly doable.
Okay, great. Here is another question. Have you had any experience with tracer testing in Bedrock? Would it help in refining a remediation design?
It certainly would, particularly if you're thinking of recirculation. Something that I would encourage though is the reagents themselves often can act as a tracer. So instead of using I'll modify that answer. The use of tracers is a good idea if you're near a sensitive receptor and you're worrying about something entering a surface water body, for example. If that isn't so much of an issue, then it could be that you can use one of the reagents as a tracer, because using something like 3DME, for example, you will start to see changes in redox. You will start to see changes in pH with, say, something like Petroclens or Regenox. So there would be geochemical indicators that would indicate if you've successfully distributed that product. But it certainly can add some value, and it's something that we could discuss on a site-by-site basis.
Okay, great, thank you. Right, this is another one. I noticed all the case study you showed were of dual porosity sedimentary rocks. Why is that?
That is that is because, well, a lot of them were in the UK, and that is because here in the UK, chalk in particular is often sort of a highly protected aquifer, principal aquifer. So there is very much a need to remediate and preserve the groundwater quality there. We've certainly done sites with crystalline bedrock. It is slightly more rare, often because it's been decided that there isn't a risk, because it may not be a important groundwater resource, for example. But there's certainly ones out there that we could have covered.
Okay, great. Well, I'll just have one more final one. This has just come in. It says here, we have a site with a crystalline bedrock where there is clear evidence on M&A at 15 to 20 meter, but no indication at 7 to 10 meter. Any idea what would be the likely cause?
It's maybe different fracture networks. You might have that's a really hard question. It might be that without seeing the site, it would sound to me like perhaps you have something that is diving, taking nutrients that from weathered bedrock and maybe even some organics from from the surface and maybe pulling them down that is enabling that M&A to occur. It's yeah. Sorry, Amanda, did they say what the contaminant was?
No, they didn't. No,
No.
sorry.
So it will depend on the contaminant. I mean, my contact details are all up there. So if you want to send me some information on that site, please do. You've got a QR code there as well. We've all got used to those during COVID, or certainly have here in the UK. So if you want to connect with me and ask me any questions directly, please do.
Okay, great. Well, I think we'll leave it here then. Thank you very much, Jack, for your presentation. If your question didn't get answers, and I see there's still questions coming in, so just to say, don't worry, we will follow up with you via email within the next few days. So thank you all for joining us, and enjoy the rest of your day. Bye.
Thank you.